Good morning, everybody. Welcome to today's presentation. So I'll be presenting about the shape dialect, and so some of you might have seen some of the work going on upstream in this, and like we had a short RFC. But sort of for this presentation, to just give an overview of what it is, what we have in mind, and how we're going to use it. So like the why, talk about some of the op-shape interfaces, what is a shape dialect, and where it will be used. And so importantly, this is, of course, still work in progress. This is not a presentation of something that is like done and dusted. And so very much looking forward to some feedback, whether in here or offline on this course. And of course, if you actually want to get involved and help build some of these things, please, contact me, and looking forward to it. Okay, so why? Well, shape functions are widely used. They're used in memory allocation, in optimization, in error reporting, in cost models, in kernel selection. They're used by many dialects and offsets. And of course, we also have many different shape functions. Now, importantly, given all these uses, we don't actually want to require duplicated specification of the shape functions just for every use case. We want to be able to reuse one specification in all these different use cases, even though it might have to be specialized for the different implementations and different constraints. And so what I'll be presenting today is sort of like the two components we have at the moment. One is sort of like the op interfaces used to drive some of the shape inference work, as well as the shape dialect. And I'll also explain actually how these two interact. Now, firstly, towards the op interfaces, there are two op interfaces and one trait. One is the inferred type op interface. So this is an interface that says an op has methods with which to actually compute its return type. So this interface is very similar to the general build method. So given operands, attributes, and regions, return the return types for the operation. And so from this interface, what we also do at the moment via ODS is we actually create custom builders. These custom builders enable you to not specify the result type and take advantage of the operations interface that computes the return type. So when you create, it effectively just passes all the operands and attributes along, infers return type, and then creates the op. It's also used for verification that the result type is compatible with the inferred return type. So given an operation that's already in the graph, run the inference and verify that the predicted type is actually compatible with the current state result type. The other one we have is the infer shaped type op interface. So this is similar in a way, but also different. This is an op that has an interface method to compute the components of the shape type. So the shape type components effectively are like shape, the element type, and an attribute. And so the difference between this one and the previous one is it may actually return unknown or null for each of these elements without the inference failing. So where in the previous case, if you fail to infer the complete shape, the function would fail. In this case, you could, for example, just return the shape without the element type or attribute without it failing. So it's a little bit more, allows for like partially passing through information.
So Jacques, is it correct to say that the previous one is sort of inferring the static shape information and this one gives you dynamic shape information?
No, so the previous one in a way is more general because it's any return type, whether shaped or not. Mm-hmm. So it's saying, well, there is a function where just given the operands, attributes, and regions, we can return a type. This one is specialized for like shape. You can sort of see this as a subclass, specifically for operations that are actually shape type. Mm-hmm. But you can also see it as, in a way, being not complete, right? Okay. Because from just the shape and element type, you cannot actually compute the, like if it's a tensor or whatnot. And let me just see, Vinod had a question about what are element types? Well, so these can actually be either of those. So if you look at shape type, the type, it has a couple of different things that it allows as element types. So this includes like the primitive types, but it also includes like dialect-specific types, right? So you can have a tf.string, and as long as the dialect actually supports a way of adding it in a shape type, it is supported. So like if you have a tensor of 10 by string, you can still use this interface. But as I mentioned, this is not complete because, for example, it doesn't sort of specify the container type. But it does also have a different one, and that's to your point, where you can actually reify the shape computations. And so this is one where insert the computations needed to actually compute the return shapes sizes. And in this case, it's like one shape return per op result for its computes. And then we have one trait, which is the inferred tensor type trait. And so conceptually, you can think of combining the inferred shaped type op interface and the infer tensor type sort of gives you the type inference for tensor type ones. So because it's combining these information about the shape and the element type to be able to infer the type for tensor operations. Now, of course, as I mentioned, there's no actual requirement that infer shape always gives you all the components you need. So it's still slightly orthogonal. They do signify different things, but it's sort of like useful to be able to combine these different ones, and so enable like computing shapes while also having the more general type inference interface. But of course, we don't actually want to write those, meaning like these are lower level interfaces used for building verification. These are C++ functions that like people have to register, but it's still duplicate information. So between like thinking about the shape op interface, for example, like why not just reify and constant fold instead of having a different interface to return the shapes, right? And of course, what about users outside of the compiler? We want these shape functions to actually be usable and be in different places, one of which is in the compiler and building. And that's sort of what led us to like, well, the shape dialect. Well, and this shape dialect is one of the things where we want to be able to express shape functions for operations independently of the dialect, the consumer, so whether it's at build time, shape inference time, or runtime, and potentially independently of the language. So we don't want it fixed to a language, but we want to be able to reusable from multiple different language front ends. And so I always talk about these as shape functions, even though some might think about it more as like metadata functions, because it's not just the shape. But I feel metadata is a little bit broad, and shape functions sort of carry the connotation of, what's the main use. And so this is sort of where we start with the shape dialect, and which we're currently iterating on in the open. And of course, like I mentioned, like these functions for these different consumers should be specialized differently, right? There are different constraints, and there's different actually types and everything at all of these questions, in different frameworks. But just because these functions need to be specialized differently, we don't necessarily want to make that sort of the descriptions need to be, right? We want to be able to have one description that we can use in all of these places. Okay, and so you can also think of these shape functions as effectively specifying constraints. So it's less that it's an imperative formulation of how to compute, but rather a specification of constraints from which we can derive the computation, but also use it in different formats. And so to give an example, like if you think about like one consumer, like the runtime, well, you can have a runtime that can only infer shapes when all input shapes are known, or one that requires all input values are known. And so like there are different trade-offs in terms of how accurate the computed shapes will be depending on which of these are known. But what we also want to do is we want to actually be able to reify and constant fold these shape functions so we can actually partially specialize it for the different cases and for the runtime. So we want to be able to take advantage of any known information at compile time or like op insertion time, but we can actually minimize the ops needed to run. And so this is sort of an example where we use this general specification to be able to take advantage of it in like this runtime setting. And of course, there's also the question of like propagation. We want the shape function normally there's information shared between multiple different ops. So for example, if you have a couple of like std adds, and I use std add because, well, it doesn't have broadcasting, so it makes my life easier. And we see like X, Y, Z getting added in this tree. Well, then as we look at the different ops and infer the shapes, we can actually start finding out what values of the indices, whether forwards or backwards, some of this gets propagated. And I sort of mentioned this not to say that we're doing either of these, but just to sort of show how they either flow upwards or downwards. And it's sort of interesting, we can go from left to right and actually have values propagate quite far along a different chain of operations, but like backwards and forward propagation. And then even when we have gone down, we might actually have to go up and reevaluate shape functions unless we do something like using like symbolic equality constraints, such as, for example, grappler uses to get to the final state. So, and I just want to mention that, so, and I'll talk about this a little bit later, like whether we do backwards or forwards is sort of agnostic to the shape description, the description of the constraints and how we utilize it. But one thing I'm quite interested about is, if folks have a model in which backpropagation has a large impact.
All of them have backpropagation.
Okay. Shape factor. Yes, okay. yes. So just curiosity, I've been trying to find ones where, for example, in training, it's often the case you have your while loop, and so the fixed point iteration gives you the same thing, even if you're just going forward. So I'm sort of curious about models people use where this has quite a large impact, but we can discuss that offline. It's just to sort of, I feel it should. I think it's very nice for error messages, for everything else, but, I haven't found interesting one which is like a really large impact.
I have a question, but should I leave it to the end? So in this case, you're talking about that add happens, so X is actually 10, 5. But you know that only if the add executes, right? Or so if you had if some condition and then add, then you couldn't propagate out of the.
So you're saying like if you have conditionals, then you're right. You have to be more conservative in terms of what shapes you can perform. In case of if, for example, depending on which if you have, if it's like the TensorFlow one where there's a constraint on the then the else branch returning the same values or compatible shapes, I mean, you can say more, but you're right. You may not be able to say exactly.
I see. Okay.
Okay, and so I'm going to give an example of a shape function and discuss a little bit of how we would represent it. And this is slideware explicitly. Want to make it all fit into like a slide. Most of these ops do not yet exist in the in open source. So of course, all of them will be actually discussed, and except for like reduce and join, all of them will be discussed there. And so, but just for this example, just to sort of show how it would work. But
looks like we have a question on the.
Yes. So does propagation work for loops? Yes. And this comes back to another question of this is based on do you do the fixed point iteration or whatnot? Again, that's sort of orthogonal to the shape representation. But for example, if you have a while op and you want to express its shape function, then that is something that you can do. And how you do it in terms of, do you say, I'm just going to do one pass through, and if I get some amount of shape information, or it converges to a fixed point versus, it's you can, for example, say for a while, I'm only going to return unranked everywhere, which is correct, but, very, very lax. Or you can try fixed point iterations to actually see how many of the shapes can you determine as accurately as you can. But a good question. So, in this example, let's actually start with the types. So we have a couple of types in this shape function. The first one of it, which is value shape. So value shape is actually a tuple of value and shape, where the shape of the value is conformant to the shape. And so it's sort of interesting you have this tuple, but that actually enables you to say, I want to express a shape function that could depend on the value, but I also want to be able to specialize it for cases where I either don't know the value or I would not want to wait for the value to be known, in which case the value is just unknown. And that we'll see later, for example, in this example, how that actually would affect the shape computation.
So doesn't a tensor know its shape?
Tensor knows its shape if it's been computed.
Oh, okay.
So this is a case where an operation produces some shape, but until you actually compute the operation, you don't actually know its shape.
I see. But in this case, so value shape has some redundant information.
Correct. It has redundant information in the case where you've already executed its producer.
Or at the point when the producer will execute, then you.
Yes. Depending on the ops, yes. Yes. So, but you're right. It does have some redundant information. We have a shape type. So this is roughly, you can think about it as a one-dimensional unknown of index. Well, of course, except a tensor of index isn't legal, perhaps not yet. And that's a different discussion. But even closer, you can think of this shape type as a status or of an any of a one-dimensional tensor or an unknown value. So it actually enables you to specify I don't know, or actually it's an error case, and propagate through the graph. You have the shape size, which, well, represents the size. So this could be a dimension or a rank. So this is roughly a non-negative index value or an unknown or an error. And then the last one is what Winard also asked about is like the shape element type. So effectively, this is just like what shape is allowed in a shape type. And this is, sort of to compute the final like value, like shape type output. And so you can see also in this case, actually shape type is the output of this function. Now let's go to a couple of ops just using this demonstration. So like shape unknown like, this is effectively an operation that gives an unknown shape that is constrained to be similar to, in this case, shape. So shape in this case is a value shape, which means if shape is known or has a known shape, then shape has the same shape. Well, actually, the output 1 has the same shape as as shape. Unfortunately, I use the same names as the operation, and so that's a little bit overloaded. So it means that, for example, let's say it is known, then this will give you an a ranked tensor, a ranked shape of unknown values. So if shape is 5-dimensional, this is 5, question marks. If shape has nothing known about its shape at all, well, then this is just an unranked shape. Then we have the join operation. The join operation is effectively what is the most constrained output shape of these two input shapes. Now, in this case, given we're doing the unknown, this is effectively representing a constraint on the two ranks of the two operators of this function. And so you can say these two ranks have to be equal. So, for example, if one of these are unranked, then the other one is ranked. Now we know that 3 has the rank of the known one. If these two operators have different rank, well, it's an error. And so for errors, you can actually specify an optional error message on a lot of these operations that represent constraints.
So is this supposed to be the shape function for the reshape op?
Mm-hmm.
So
which it may actually have a bug in the loop, but yes.
Yeah. So I guess isn't the rank of tensor has to be equal to the length of shape, right? Because shape is actually a 1D tensor.
That's true.
So
that is true. You're right. You're right.
I think there's like a little.
You're right. You're right. You're right. Yes. This would be the length of shape. Good point. And so in this case,
question.
This is kind of unioning the two shapes, is what effectively was
doing.
Yeah. So unknowns get filled in.
Yeah. So in your shape dialect, broadcast is explicit. Yes, we actually have a broadcast operation. So you can actually say like, give me the broadcasted shape of these two input shapes. And so, of course, for a lot of these cases, you can auto-generate an error message that like looks at the expression trees of its operands. But in a lot of cases, that doesn't really give you nice error messages. So, like, you have an optional error message string that you can add. And I've been thinking a little bit about the error interpolation there, but nothing actually implemented. But just so you can actually able to surface higher level information that the user could act on along with the error message, even though you're expressing it in the shape function. The next operation is actually one of my favorite ones, value as shape. This is one I needed for the full operation as well. So this is effectively saying like, if shape is a one-dimensional tensor of, and the value is known, of integer type, then return a shape. And so it means that if the value is not known, like VS just becomes unranked. If the value is not a 1D tensor of integers, it's an error. And if it's an error, like this VS value now, in all the places it gets consumed, just gets propagated forward as error cases without actually evaluating any of them. But if it is a shape, now you have a shape which is potentially unknown, potentially unranked, that you can use in your succeeding operations.
I'm having a little bit of trouble keeping the two concepts of what's at compile time and what's at runtime separate, because at runtime the value will, like VS would always be a concrete shape.
No.
Right? Okay.
It would only be if you only evaluate this function after the producer of shape is completed or this value of shape is known. So you can also actually evaluate this function or part of this function before the actual value of shape is known. And even at compile time, shape could be a constant.
Right. I mean, that I understand.
Yeah.
But like it's not. So when you say it's VS can be unranked, unknown, it can actually be that even at runtime because
correct. So depending on, And so at runtime, you may want to decide, like, okay, you know, I'm going to actually add a constraint to this function that it's only actually evaluated at the point where the value is known. In which case, yes, value as shape always returns either a 1D tensor or an unknown, or an error, sorry.
In some way, that means like we decouple the expression of the shape function from its usage.
Yes.
And you can say, I want to instantiate this shape function in the context where I want the exact shape. In which case, like, yes, you have constraint on the value being available. But you can also say, I just want like the statically approximate shape, whatever you can do right now.
But usually the way I've, so this is actually very interesting because like the way I would have normally done it is that you would only have this one way of in writing a shape function, which given the exact input shapes gives the exact output shapes. And then
because you want data flow analysis.
Yeah, and then you would do data flow analysis on top of that to say that, well, if you know the left-hand side shape but not the right-hand side shape, you just invoke like standard like value propagation or whatever to induce this approximate shape function over it. So I have to think through like how that.
I think this essentially is that, except that it also is trying to capture the case of expressing constraints on the inputs as well, so that you can say, for example, like, oh, these mapmol, like this dimension have to match, which like a standard date, you know, because like if you just have like a simple forward calculation, you would be like, well, I'll assume these match, and then.
Well, I mean, that's not any different from saying, well, the shape function will have assert, where assert is like it either has undefined behavior or like throws an exception if they don't match, and then you would write a data flow analysis that says that, well, let me find necessary conditions for this shape function to not throw an error.
I think that's what this is, except for that essentially, like Jacques was saying, there's like essentially like a status or all these types kind of and so basically it allows you to just do it with like diffuse chains instead of having to like literally like look for like.
Right.
There's also another difference, right? Like you guys seems to be talking only about the shape as a metadata on every tensor, while here, and especially value as shape, is a way to save on every input. You can also express that your shape function can look up the actual content of the input tensor on some of those inputs. And that's different from just saying it's like operating on some metadata.
Sure.
If you wanted to operate as you described, you would need a way to express ahead of time that actually, if you give me the value of one of the inputs, I can provide you a more accurate result.
Right. I mean, but what I was suggesting that the way you could express that is say that give me the value of this input, and that is the only way to get the shape. And then saying that, and then you would analyze that source of truth to say that, well, actually, without the value of the input, you won't get a complete shape.
What do you see here that is not like that?
So the thing that I see here is not like that is, in this case, VS can be an unknown shape even at runtime. Whereas that's the part I'm finding a little confusing, because normally I would think that, well, actually at runtime, everything is completely known because.
Well, I think that again.
You call it runtime.
By runtime, I mean like the program execution time.
Yeah, but like then yes, if you just sequentially execute thing and this function is executed at the time you need the shape and you have the input, then yes, it cannot be unknown.
Yeah,
right? It cannot, because you have
so at run. So okay, that's what I mean by run. That's exactly what I mean.
Yeah. So I think by runtime, the reason why it's ambiguous is that by runtime you can also say I want to pre-allocate things, and then in a loop I'm gonna use the results of this shape function. In this case, like you don't have the value yet, you only have done whatever you can do statically.
Yeah. And in terms of, Vinod also asked the question about are shape functions always computed at compile time or at runtime as well? And yes, at both. And so actually I'll show in the next slide some of the things we want to do where, you know, you actually want to generate some of these, even effectively sort of like that's partially specializing it for the things you already know at compile time, but you still need to do some work at runtime. And so I want this to be like you can specify it once, but use it in both these cases.
So Jacques, so kind of coming a little bit back to finish the question Sanjoy said, is it correct to say that if all of these inputs are completely known as they would be at runtime, then executing this code is guaranteed to give a fully formed output shape or an error?
Yes.
Okay, so it is essentially like a constructive specification of the output shape.
Yep. And so, for example, now we have the reduce. So this is a case where it is reduce over a shape with given loop carried variables. So you can think of it as equivalently like as you have a result, you're enumerating over the shape, and you're sort of evaluating a function with the index and the value and all the loop carried variables that you sort of override. So like in this case, you can say, well, index, and you can actually specify like what integer type you want to operate on. You have a dimension, which is the shape size, which corresponds to the ith dimension of the shape. And then you have different set of variables that will be loop carried and that will be passed through yield back. And of course, we can actually use, I think, the prettier form that Stefan and folks actually have added here to make this perhaps a little bit closer to that. Yeah. How does this work for ops where the output shape is not known? Very good question. So for ops where the output shape is not known, you have a couple of options. One of which is to say its shape function always returns unknown. But actually, unique is an interesting example because you can write a fully shape function for unique. The cost of that shape function is just as expensive as running unique. So it's a case of where you probably don't want to do that, even though you can represent it exactly this way. And that sort of comes down to, I think, one of the other points in terms of like the offering, where even though you could write a shape function for unique that would give you the exact shape, you probably don't want to. And at most, you want to propagate information in terms of constraints of the output shape with respect to the input shape. But so if you look at the reduce function here, like it says, it operates over VS. So if VS is actually unknown, the return value is unknown because it's unranked, so there's no reduction that actually makes sense in this process. And then effectively we've computed the shape at this point, and the rest of the calculation is more towards like the element type. And this function in the middle with dim at is effectively like propagating the same input shape, but by updating like a dimension. This is something which, I think we probably want to do more of like an affine map potentially in the inner or something like that. Or you could have done this with a join as well. And that can sort of just effectively returns this shape, but just with one of the dimensions updated. Element type is, in a lot of cases, quite simple. In this case, it is constrained like the output element type is the same as input element type, which you can just return. But the interesting thing is not just like the shape function is isolation, and this comes, I think, to like one of Vinod's questions as well. It's like, but what if we actually do have multiple of these, we have a graph with multiple of these functions? So let's say you have, again, this group of adds, what can we do? Well, we can actually start by like inlining the shape functions. And so now once you've inlined them, well, you have a part that computes the shape, like what is the output shapes of this operation. And then you might also have some calls for like the runtime. So which may be like allocations or whatnot, or setting runtime dimensions that are like part of the usage for a given runtime. And sort of complementary to the shape computation, which just gives you sizes. But you need to actually execute and fully lower this for the runtime. Now, of course, like with the operations, we want to optimize, so you might do some concept propagation, and effectively partially specialize from the computations and reducing the code, do some CSE to group similar computations together. Now, schedule it, so now actually you can, given the data dependencies and requirements, and given none of the add shape functions actually depend on the values produced by add, we can actually hoist these earlier. And then post some liveness analysis and buffer allocation, we can find out, hey, actually, once we've computed the shape, we don't actually need to do more runtime calls in between. We can reuse these buffers. And so now what you add it up with is actually like you can have all these computations that you need at runtime to actually compute the shape and do the allocations can be all grouped together and potentially hoisted out of hotspots. So you can hoist it out of loops, perhaps even to the start of the program, of course, memory allowing, because now once you've hoisted some of these further upwards, you are actually potentially increasing some of the lifetime ranges. But that effectively gives you the option to avoid having to do these computations along with the operations. So you can split the computations in the operations from the computations of the shapes. And so actually get some better efficiency in the lowering. So you can feel in the JIT context like partially specialized for just the computations that you need, even though you started with a very generic description of the operations. And again, this is just for these shape functions, these ops are just ops. So we can use the same paths as we use in MLIR everywhere else to optimize them. This is just a regular graph optimizations that we can do. They're side effect free, so they can be hoisted, constant folded, all of these things. Modular error semantics, where you might actually need to insert like different shapes to be able to surface errors. And so that's quite nice. But what the shape dialect, for example, does not tell you, and this is sort of a couple of other questions, it does not specify like the shape inference type, right? So this is the function as described in the previous slide. There was no mention of the direction or how we actually want to use it. So to Mehdi's point, it's like the decoupling from the specification and the use sites. And so whether you finally actually didn't have a consumer that does use it for forward propagation, backwards, symbolic solutions, that's sort of more in the consumer context. Similarly with the usage time, where it's being used when you create the ops at shape inference, so when you've already constructed, let's say, a bigger graph and you want to propagate values, or at runtime where you might actually know all the information, you can have the same specification but specialized. It also actually doesn't specify the error mechanism. So while I've represented it as errors getting propagated through until the end of the return, it doesn't mean that you can have the equivalent of after every constraint and if failed, then abort. Or if you want to do it later. It also doesn't say like if you have errors along multiple paths, it doesn't, there's some freedom in actually how you want to report it. So whether you want to just concat them always, or if you want to return an arbitrary error, flip a coin and decide which path's error to report first, which is of course not suggested, but that's something actually the shape functions does not fix that. And also importantly, it doesn't actually require a container type. So whether this is a shape for a memref or a tensor or whatnot, that is not actually part of the shape function description, nor is it specialized for a fixed rank or element type. So we want to make this as generic as possible so we can specialize and instantiate it for all of these different cases. So another good question, I showed you a nice slide where with a lot of ops that I made up. Well, so what are all the ops in the shape dialect? And I think that's very much TBD. The goal is to keep it small, and while I have some bias in terms of which ops I think will be useful, this is more a case of where I sort of want to explore it by looking at existing use cases and existing customers and see, can we define a couple of nice operations that allows us to use it in all these different contexts while not adding too many. And of course, we want to reuse as many existing ops as possible. So like if a fine map or a fine apply, we can use them in more places. We can take advantage of all the tooling and optimization already provided there. And I will sort of mention, like anecdotally, like with 10 shape ops, I can cover about more than 700 of TensorFlow's ops shape functions. So it does sort of seem like we might be able to get a good combination of like expressivity and coverage with a smaller set of operations. And actually, speaking of like TensorFlow's shape functions, I sort of looked at across all the TensorFlow shape functions, and on the vertical axis, it's the name of the shape function, and on the horizontal axis, it's the number of uses. And so if you can see, look at like the very last bullet, it's effectively the majority of shape functions are used by less than 5 operations. So it's a very long tail. A lot of operations have a unique shape function. And then our most used shape function in TensorFlow is actually the unknown shape one, which in a lot of cases should rather be the compute at runtime shape function, because it's in a couple of cases it's not like unique where it would be difficult or really not very useful to compute it before executing the op. But in cases, it's more where users either did not know or did not care to write a function to use during shape inference, given what they were seeing at runtime. And so they were happy with what they had already. But I think that's sort of interesting because I would almost combine some of those unknown shape functions along with the other ones. And so I feel like there's a couple of ops like scalar shape, awesome, right? Returns just a scalar, beautiful shape, easy shape function. There's a lot of like unique shape functions. And so it's going to be quite interesting to see like how many of those can we cover quite easily and perhaps mechanically by just a small set of shape functions. But I've not mentioned at all at the moment is authoring. How do we actually write these shape functions? How do we write the shape dialect? Well, there's a couple of avenues of sort of interest here. One is via the ODS constraints. So in ODS, we already have some shape constraints being expressed along with operations. So for example, same operands and result shape, which is, effectively gives you a unique indication of what should the output shape be given input shapes. And of course, we want to be able to share some of the constraints for the declarative ASM with this. So like, if people specify, effectively try and get as much reuse as possible between all of these different approaches where we're looking at shape. The declarative assembly is not shape specific, so it does allow things which the shape dialect would not. Then of course you can actually write the shape functions in the shape dialect directly. Now, this is of course the normal caveat. The IR is not a programming language, but in my biased opinion, it's also not terrible to read. So I actually, find it reasonably readable. But again, probably my bias.
Well, and also because we kind of get to decide what ops they are,
Yep.
and so we can keep it pretty minimal.
Yeah.
That's
true.
Yeah.
Of course, there's the option of actually generating from a front-end language, potentially like from Python, Swift, some DSL. I think for me, it's more like what we use it for afterwards, and the optimizations and passes we run on top of it. But the most desirable one would actually be to extract these shape functions from the op definitions. So this is so that we actually have the same source of truth for the reference implementation, for the operation that we will be optimizing and we will be generating code for, and I can also extract the shape function for. And so, for example, from linalg generic, this actually seems quite nice because it's very expressive in terms of its input-output spaces and operation dimensions. Other operations, it may be more difficult, so it's a gradient. And I think that's sort of where the ability to be able to specify them directly as well is quite useful. Some next steps, well, more shape ops. Effectively, I think I've got 6 or 7 externally at the moment. And, so a couple more of them landing and expecting, of course, all of these will be sent for like normal review and discussion on Fabricator. Of course, if folks have suggestions, I have ops that I think are quite important, awesome to discuss either there or on Discourse. So the lowerings to standard and affine and linalg and et cetera, et cetera. So effectively code-genning some of these shape ops. And I also mentioned actually the reified test case I added in core at the moment is wrong. It's sort of just an example and to test the interface rather than an example of what we should have there. So that will be changed. And of course, I want to actually add more consumers. At the moment, the only consumer of these is from like ODS and for using in the build method and create and for forward propagation. So adding some passes to actually do some shape inference, maybe just starting with like a simple one. And then also, actually, I would love to do one where we actually emit like a Z3 solver-esque formulation for some of these functions, just to sort of avoid us overfitting for some of the simple cases in our uses. This is not something that, we'll be, I think, using immediately, but I think it would be nice to just verify that we're not creating operations which would make our lives harder in some of these contexts. Actually, one of the things I forgot to mention is also there need not actually even be one shape inference you run over all of these. You could have like different islands where you have different kinds of information. And so, for example, you have an area where you're using all affine operations and you have more exact shapes and more exact constraints interacting with more black box-esque operations. And so, it will be interesting, like this barrier where we try to do more like tongue-in-cheek multi-level shape inference would be quite interesting as well. But that's perhaps a little bit further along and maybe a little bit more on the researchy side. And of course, I want to battle test some of these on offsets. So like TensorFlow is a nice offset to battle test on just because, there's a lot of TensorFlow ops and some of them are quite weird. Some of them which the resultant type is actually a function of the element type of the input. And so it's quite nice to sort of just verify the expressivity and the coverage. HLOs is a much nicer set from that point of view. But yeah, so quite a few of those. Anyway, this was sort of quick run through for some of the shape dialect, the shape inference ideas, we have there, as well as just sort of talk about like things I have in mind or we have in mind and directions we're in. So that's my last slide. Okay. And I think we also don't have any questions on the agenda, Doc, but if folks have some, either add them there or unmute yourself and ask.
So I have a question. Which I already asked you in the past, but
Can you speak up a little bit, Mehdi? I don't know if you're
Sit here.
being
Yeah.
on the mic.
So something that's interesting me is like in a lot of the unknown shape function right now from that you survey from TensorFlow, or even like most cases that cannot be handled like NMS or unique, we cannot return a shape without doing the computation, but we can return a maximum shape.
Correct. Yes.
And today, like it doesn't seem like those shape function have this concept of propagating those bounded.
Yes.
I think this comes back to what Sanjoy was saying, is this approach of materialize or reify a constructive procedure for calculating the exact shape and then doing data flow analysis on it, which is basically what's happening here. That is that approach is limited, right?
Yeah. So actually, one thing that I don't show.
I mean, it's a good sweet spot, I think. It just doesn't cover everything.
Yeah. So one thing I don't show, and that this sort of actually comes back to like the first part of the shape type components, and that is the attribute. And so this is one of the things we've been talking about in terms of like tensors having an attribute associated with them. And so, for example, for the boundedness, this could be part of the attribute that you actually finally produce. But you're right in this case where you have the shape, the boundedness constraints that you want to propagate. This could, for example, be like a comparison on or an assert on the maximum size that you represent gets propagated through. So
I think we can layer this pretty well, because like the approach of materializing the shape calculation, doing data flow analysis on it, you can choose a particular data flow analysis, which is give me an upper bound, and then that layers nicely as like a subcomponent of like a functionality which gives you upper bounds in general, which like your JPEG decoder offer, like whatever like you might need to. So like I wouldn't try to shove too much stuff into this particular layer.
Yeah. So
There's a bunch of discussion in the chat. I don't know what you
read it out.
Yeah.
what you covered during the talk and or not.
Yeah.
This is new. Oh, can we not scroll back further than that? Okay. Well,
No, I can scroll back further. I just don't know when did you.
This is the last one we answered.
Do folks that are in the chat want to
Stella, maybe you
turn
want
on the
to
mic?
talk about?
Yeah, sorry. A few of us were going back and forth in the chat a little bit. Let me try to refresh. The root question was from Medor. Will it ever occur that you infer shapes at compile time, but at runtime it becomes invalidated due to additional info? Does it involve a conservative approach?
So, I mean, it has to be conservative. So, I mean, like if you're at compile time, effectively, if compile time result gives you a different one that's not compatible with the runtime one, and you had an error, right?
Yeah. So I think we bias towards the compile time producing the most general answer, so that shouldn't happen. Correct.
Yep.
Yeah. And that gets back to some of the points of it being really nice if we could also express max bounds and so on, because that's a useful generalization that happens a lot in practice.
Yep. And you're right. I think that's probably one I should add an example for sooner rather than later, perhaps starting with df unique, which just returns the boundedness and unknown but bounded.
Yeah, because there's a lot that we can do if we, the more information we have. And, it's usually a better trade-off to have that earlier.
It's true.
So I have a question regarding how this is going to be done compile time versus runtime. So if I want to do both, would you think like I should be taking the shape functions and pre-compiling them and using this for my compile time specialization and inference, and then inline them for the rest of the shapes that cannot be inferred for runtime inference?
Yes, I think so.
That's
I mean, I think, I think that's the way to then be able to say, like, we don't have to define these things multiple times. We can use the one specification, or which may turn out to be the op definition eventually. But then, yes, being able to specialize it and generate the runtime things that only needs to compute the things that are required, I think would be is the way we're planning to proceed. I mean, actually, Stella has done some work that actually shows this already in a couple of cases, and so that's actually quite nice. Like on the Erie side, it's like there's a couple of examples where that's already being done there.
Yeah, and we've been focused on the cases that are more interesting from a compiler perspective, which involve when we can infer a fixed rank for the shapes, and also there was one other. When it's not purely data dependent. So when we can reify the shape function based on the metadata that float all the way up from the function arguments.
And in that case, the shape function is kind of external to the actual code you're compiling?
We actually inline it all together currently and then hoist it to so that it runs as early as possible. And so we can do buffer allocation early and get some more concurrency.
So it's runtime checks?
Yes, as runtime calculations. There's if you typically for the ranked cases for a lot of ops, you don't have very many checks. You've inferred something reasonable. So it's TBD for us getting more into the more dynamic cases that are less fixed.
Yeah, I guess my point is that because at ngraph we have this kind of shape inference capabilities, and we don't. If you want to express it as shape functions, we would like to have this ability to do it dynamically and at compile time without having to rewrite the two parts for it. Yeah.
Yep.
Yeah, I mean, I would say. Sorry. Sorry, Vinod, I interrupted.
No, sorry, I was just turned off my mic. So why don't you finish? I was going to ask a question later.
Oh no, I was just going to say, and I mean, I was quite interested, like ngraph shape function size, to see like for shape functions how this would work, how we could express this, what operations would be needed. So very interesting to see if we could grab a couple of those operations and just sort of explore it as well. And so, Vinod?
Yeah. So one high-level question I have is, I'm still not clear about the flow of the shape dialect through the compiler passes. So let's say when you compile TensorFlow graphs into some MLIR, you get shape dialect functions. They get generated somehow, either or from some library. You get that, and then as you lower your MLIR dialect of the computation through things like buffer types and memory and all this stuff. So the shape dialect that was describing the original graph now has to be refined to a lower level, right? So is that done? Is that in the plan, or is that done automatically? That part is not clear how that happens, or it exists at the beginning but not later.
Yeah. So I think in the beginning you have your tensor functions that operate on tensor types. So you would potentially infer like the return types and specialize the graph as much as possible. But potentially you can still end up with now a couple of unranked tensors, and it's in your TF graph, and that's fine for the normal execution. But now you want to cogen it, so now you need the next step, which is to say like, okay, for the ones where I don't have all the known shapes, I need to reify them. So insert the actual computations, and this could start by actually inserting the shape functions, which to your point later on would have to get lower to like standard or linalg or whatnot, so we can actually cogen them. But now you insert the shape functions, and their output may be consumed by, let's say, a malloc, because we might be going to like the buffer version of this next. So you have your tensor operations or the lower tensor operations operating on buffers, the output of which gets populated or allocated with the malloc that is fed the inputs from the shape functions output. So now you have a graph again with like shape functions, mallocs, and whatnot, that you have to now cogen, which means the shape reduce has to get lowered to a loop for which you can generate code, or it gets folded away. And you can take advantage of the thing to say, like, for example, like if I know I'm going to be cogening this all, let's say for a micro device, I'm going to have one thread, then I'm just going to schedule it. I'm going to lower all the computations. I know everything will be known at a given point because I schedule everything, right? If you don't have that, and so if you're not just cogening everything together, you might now actually have to insert like additional weights or dependencies depending on which runtime will be run. But so I think so the flow, for example, in this case might be now, that you think about is I've reify those shape functions, they're consumed by their mallocs, they feed into their buffer functions. All of these just get lowered in parallel. So the same way you would lower the TF add to your finally LVM intrinsics or NVPTX intrinsics, you would the shape functions would also get lowered. Because at the end, they
I got it. So I think so somewhere you're going to have to do the work to lower them.
Correct.
Out of gradual lowering the regular dialects.
Correct. So yes, similar in a way they're similar to any other ops. So you have to express the way to lower them to the lower level ones, in which case utilizing the existing dialects that are already there. And so, for example, you can actually lower some of these shape functions back to the equivalent PF ops, right? And then code in them. We may or may not want to. But yes, very good point that you actually have to lower them again to code it and run.
So I think my last question on this, I think it was, is lowering of shape functions optional? Could you just basically use them in the beginning and then put them away and then just go back to regular?
Yep. Yeah. Exactly. And so I think this comes back into like the interface. So for example, your op type or your op type shape interface could literally just interpret the shape function, give you values back without actually instantiating ops. And boom, you have your shape that you've computed and you go on. You don't actually have to insert it in the graph. So you're right. So you can take advantage of what shapes it produce and use that information where you normally would, but it doesn't actually have to go to ops.
Okay, thanks.
So, Jacques, I had two questions. One was, it seems like this is is actually a small step away from actually having a full first-class type system expressed as a dialect. So why do this just for shapes? Why not just do it for everything and then make it kind of orthogonal and generic? And I think some of these questions about how do you do reification is really how do you express type inference, and how do you do what are the guarantees that you have? Are these conservative or sort of should become soundness properties in some respect?
You're 100% correct. I'll be honest. I was hoping nobody notices it's so close to type inference. At one point, I was thinking about referring to it as a type inference dialect. I sort of backed off a little bit because I think a lot of people have a lot of different views and they want to use, for example, different kinds of type inference, for example, dependent types and whatnot that may get us into, I think, longer discussions. It's still very good to have. So I sort of felt after the shape one as a step where like reifying shape computations is normally computing algebraic values, right? So you have output of integers, which seems, it's a little bit easier to conceptualize than reifying should the output type actually be a struct of these things or not? So in a way, I agree with you. It was one sort of for more simplicity into starting off from. But this is definitely something I would love to explore a bit more in the future. But yes.
The other question I had is it doesn't seem like there's actually any in-tree users for this other than ODS.
Correct.
And the compiler, the compile actually breaks, I think. So maybe you can just at least add an in-tree user and get there's nothing that actually includes the ODS files.
Well, except for the test dialect. So the test dialect, there's a couple of ops that it does the infer type one and infer shape one. And I think we landed one on TensorFlow side this past week as well.
Okay. Well, I'm not looking at the TensorFlow part of it, so I'm just looking at what's in the MLIR.
Yeah. But no, I was just it's curious about the breakage. Please think about that because I thought we were actually testing all of those. So if it's not failing to compile, then it's
I'll ping you again.
Awesome, thanks.
Jacques, is there anyone on your side planning to do the lowering of these shape functions to the more fundamental dialects, or is that TBD still?
That's what I was presenting. Yes. So we are actually going to do a few of those. So I'm working with Alex, and so he's thinking about. We've been discussing like lowering of a couple of these down to like standard affine. I think he has a deadline for something else this coming week, but hopefully next week or so we can actually land these so that, because I agree, like at the moment the Reify one inserts the dim op, which is completely wrong types, wrong everything.
Yeah.
So yeah, definitely, yes.
Okay, thanks.
Okay. Thanks everyone. I think we have about a minute left, but please ping me afterwards or on Discord or whatnot, and we can continue the discussion. Awesome. Thank you.
Bye.